reaction. In this lecture, we can simply separate into three parts. The first one we call the fluid-solid chemical reaction. Fluid here included the gas or the liquid form. So can be a gas reacted with a solid or a liquid reacted with the solid. So the example here we want to show you would be the oxidation of silicon substrate, which means the formation of native oxide. And the solid here, we will focus on the flat interface or flat surface, which means the solid here will be the substrate. And the reaction is majorly happen on the surface of the substrate. And the second section we are going to talk about will be the fluid chemical reaction. So can be the gas react with liquid or two insoluble liquids. So gas reacted with a liquid can be used can be something like you try to use a liquid to remove certain specific gas out of the mixture gas. For example, if you want to remove the carbon dioxide from the mixture, then probably you can use the carbonate, okay, or hydroxide. And this is the table to show you, for example, like if you want to remove the NO from the mixture gas, then probably you can use this solvent, okay? And regarding to the insoluble liquid here, I also want to give you an example, would be the glycerol. If you use the glycerol dissolved in nitric acid, then you can get the nitroglycerin and the water. So this is I'm not sure whether you know what's the nitroglycerin. Actually, it is explosive, highly explosive. Can use this as a bump. Or in medicine, some people use as a vasodilator. Okay. So to expand the vein or the blood vessel, to expand the blood vessel. Okay, so this is we call the chemical reaction happen in two insoluble liquids. So in this part, no matter it's first one or second one, we want to highlight one important thing is in heterogeneous reactions, we don't only consider the reaction, how much time happen in reactions. We also need to consider regarding to the transport part between two different phases. So the total reaction rate included the transport part and the reaction part. But compared to the one we learned in lecture 6, the rate equation, you only focus on the reaction rate, right? Reaction rate, right? Because everything is happening in the same phase, so you didn't consider the transport part. But in lecture 7, we do have different phases involved in this heterogeneous chemical reaction, so we need to consider the transport and reaction. And for example, if we talk about the oxidation of silicon substrate, which means you have oxygen, right? And oxygen need to transport to arrive on the surface of the silicon substrate. So we will have the transport part, and also as long as the oxygen arrives the surface of the silicon substrate, it can start chemical reactions, right? So you have this transport time and plus the reaction time, and you need to see which one is faster. This faster, or it both spend similar time. So in this case, in order to see which steps is limited step, and we use the resistance to show you or to use as an indicator to give us a quantitatively indicator or quantitatively idea about how much time is spent in transport and how much time is spent in reaction, which means this faster or less faster or both. You also when we estimate the rate, reaction rate, I mean the whole heterogeneous chemical reaction rate, you need to consider both. Okay, so the rate equation for different transport resistance and reaction resistance, based on this value, you can know in your interest in heterogeneous chemical reaction, the weighting for transport and reactions is what, which is the limited step or something. So the detail we are going to talk about in following slide. And the last one actually is we call the fluid particle chemical reaction. But in this case, some people probably will consider particle actually also a solid, right? It's also in solid phase. So the particle part here, we will focus on the particle's diameter, how the particle diameter affect the reaction rate. So here we are going to propose two different models. In this case, the one we call it, the first one we call it a progressive conversion model, and the second one is shrinking coal model. Progressive conversion, the characteristic for this one is the particle size is not going to change during the heterogeneous reactions, but the product actually will the thickness of product will get thicker and thicker, but the whole particle size does not change. So which means it seems like this. For example, the particle size was here, right? So our product actually will get thicker and thicker in the beginning, probably like this, and then get thicker, which means our product actually directly form on this particle. But the shrinking coal model means the particle actually, the gas react with this particle, and this particle size will get smaller and smaller. So this is we call the shrinking coal, which means the product probably will generate some gas phase, and it will diffuse out. So that result, our particle, the diameter of our particle gets smaller and smaller. And in this case, we are going to show you how to formulate and find which is the rate determining steps and corresponding rate equations, and we'll focus on the size, what's the size of the particle as a function of time. Okay. So let's move to the first one. We are going to talk about the fluid-solid chemical reaction. So before we move to the details definition for heterogeneous chemical reactions, but we want to highlight the importance for these fluid-solid chemical reactions. And the case we are going to talk about would be the silicon oxidation kinetics. The gate oxide or native oxide actually is very important in MOSFET because it serves an insulator to separate the gate and source and drain, right? So here actually highlight the detailed process, how we built the MOSFET device. And the first step actually is to form the gate oxide. So it will be quite important, right? It is a first step, and will be the silicon oxidation. So here, we want to, depending on different process, but the thickness of this gate oxide can range from 5 nanometer to 200 nanometers. So how to estimate the growth rate? How to predict the growth rate for this oxidation process will be quite important and very interesting. So this will be our case here. So let's back to talk about what's the heterogeneous reaction. Based on the definition, you know when more than one phase is presented in our systems, the overall rate equation must consider the phase-to-phase mass transport and the chemical reaction kinetics. So you need to consider transport term and also reaction term. So let's give you an example here. We have a solid carbon react with gas oxygen, and we were going to generate the carbon dioxide, gas carbon dioxide. In this case, I try to draw a cartoon here. We have air here, and this is a solid carbon. And in between, I will call it is a transport layer or thin layer. So the oxygen will be in the air here, right? Oxygen need to diffuse through this thin layer or transport layer, then it can arrive on the surface of solid carbon. Belongs to this one, right? And it will react with carbon and generate carbon dioxide. Then this carbon dioxide need to leave the surface through mass transport or through diffusion. Otherwise, based on the Le Chatelier principle, in this case, the accumulation of carbon dioxide will affect the balance of these reactions and will impose the change and re-establish the new equilibrium, right? So in most of cases, in order to allow this reaction go to all the way to the right-hand side, the carbon dioxide need to leave the surface during process. So based on this, we have 3 reactions or 3 processes, and they belongs to series reaction. And my question would be, they are series means the carbon dioxide, but so other oxygen need to diffuse through the surface, right? It spend time 1. So let's try to. So probably this will spend T1, and reaction will be T2. Spend T2, and the carbon dioxide left the surface will be T3. So when you want to estimate the overall rate equation is overall, right? It will be T1 plus T2 and T3. So in my question would be how to model this kind of series reactions and tell people which process is the rate dominant process. Which one is faster or which one is slower? As long as you know, series reaction always slowest one will be dominate whole overall rate equation. So here in your textbook, actually they give you some ideas. You guys did learn the electrical circuit, right? For the electrical circuit, actually we have a driving force will be the voltage. And as long as we have a driving force, and that will lead the current passing through whole circuit, passing through each resistance. Okay, so the same idea can be considered here. Who will drive these reactions will be the oxygen gradient, because oxygen for sure is higher here, and when it arrives on the surface of carbon, it will drop to 0 because we assume the oxygen be consumed completely. So this concentration gradient will drive the flux, right? So the oxygen flux passing through the transport fin will be equal to the oxygen flux react with the carbon. So this will be the R double prime actually is the flux. And resistance will be what? I have a resistance in transport layer and also reaction layer. So resistance means what? the transport, you have like the oxygen transport fast or slow, but we use a resistance to represent it, right? And also the reaction, also this reaction is fast reaction or slow reaction, we use a resistance to represent it. For example, if transport fast, that means resistance is small, right? So they have like a reciprocal relationship, right? And if fast means the resistance is small. So we use this resistance concept to present, to quantitatively present how much time or to describe how fast or how slow this step is in this series reaction. Okay, so today we just ended here.